start off, as I said, with a 3.0 industry update and technical overview. Just to set expectations, we assume for these presentations and our discussion purposes that you have some base level of understanding of what an S parameter is, of what de-embedding or embedding is. If you don't, you can go to several webcasts and seminars that are available at this event as well to try to increase your knowledge and the basic application of these measurements and the S parameters and the basic techniques that we're talking about. But for USB 3.0, I also assume that you're familiar with what it is, but I will go through some of the key technical bullet points as a comparison to 2.0, mainly to focus the discussion on why do we need to test it the way we are today because of the changes that are different from 2.0 and how serial interconnects have worked in the past traditionally. So let's go through industry update and kind of an overview of the super speed development timeline. The spec's been out for quite some time now, released in 2009, but product development suffered the whole economic downturn just as everyone else did, and it kind of slowed down the adoption as people were both saving or holding off on investment in a new technology as well as waiting to see what other standards that were announced around the same time might do. But now USB 3 is going on a very steep ramp with all the major chipset OEMs announcing plans and product roadmaps that include USB 3.0. So the key spec that drives our test requirements is the test specification, which the first draft was released publicly early last year. So that is not at 1.0, but we're close to 1.0 on the test specification. There's just some channel modeling questions that remain to be formalized before we can go to 1.0. We have been certifying products since Workshop 72 last April at workshops and at the Platform Interoperability Lab. That's a test lab at Intel that has all the test equipment that we will talk about today to do transmitter and receiver certification. But we've had 5 events now where we do certification of products. There was one last week in Hawaii. Unfortunately, I had to go there to support it. But that was well attended. We certified we tested over 30 super speed USB products at that event. And the next one's scheduled, sorry, Fetz, if I shoot you in the eye with this. The next one's scheduled Workshop 77 in Portland, Oregon, where we'll continue to do test procedure development and actually qualify test labs for certification at their test facilities. And that'll be a key gateway for mass adoption of 3.0 because then people can get their products certified. They can engage with the test labs for advice and design guidelines in the local environment. So now let's go through some technical differences to highlight why there's a test methodology shift on high-speed serial interconnect testing. USB 3 is the first standard that I've been involved with that is actually formally requiring embedding of a channel for your physical layer transmitter test. So obviously the key difference between 2.0 is the increase in signal rate up to 5 gigabit per second with almost the same channel length. So that takes and it greatly increases the challenges that interconnect designers face if they're going to run a much faster signal over the same physical length and materials. So it's 8B, 10B, PRBS, full simplex. If you're familiar with PCI Express, electrically it looks identical to PCI Express Gen 2. However, in the cable and connectors, you actually have 8 signals that run in parallel. You have the transmit and receive for super speed, as well as all the USB 2.0 signals. What this means for interconnect testing, which Mike will talk about in more detail, is that you have a greater chance of crosstalk issues that will manifest themselves in degradation of your signaling. The cable length for super speed is roughly 3 meters. It's not a physical length that's defined, but it's an insertion loss target. But that's the practical limit versus 5 meters for USB 2. That's still a significant length of channel. And then the FR4 for the full channel, that would be the host plus the device traces, is roughly 16 inches for a super speed versus 25 inches for USB 2. Those are still very close for a 10x bump in the speed. So again, the modeling, the measurement, and the simulation of the channel and interconnect behaviors is going to be a very important step in your design process. For transmitter compliance testing, SSC, or spread spectrum clocking, is a big problem that device developers have faced in passing certification, because they have to generate this spread spectrum profile and do it in a well-controlled, modulated rate that meets the spec. And the biggest change for transmitter testing compared to 3.0 or USB 2.0. 2.0 measures the signal right at the transmitter pins with a short breakout fixture. But it makes the assumption that the fixturing has negligible effect on the measured signal quality, and the eye patterns are designed with enough margin in them to account for interconnect differences. Super speed cannot make that assumption. So the transmitter is characterized at the far end of the channel, and I'll describe it in a bit more detail what that means. But basically, you're measuring through a nominal case channel of 3 meters of cable, and for a host, 5 inches of FR4. And then receive jitter tolerance, which is also run through the same channel definition or fixtures, is performed, and it's for receiver testing for 2.0. There's no official test modes required for host certification. For 3.0, it's an exhaustive jitter tolerance test. You apply the amount of jitter at the sinusoidal and random jitter components that you want to test to. You derive the device receiver into loopback, and then you look for bit errors on the output of the device under test. So I said the transmitter is characterized and certified at the far end of the channel. So on the right hand of the screen, you have your device under test, and you connect it up to a scope or any 50 ohm passive load, and it is required to detect that low impedance path and go into compliance mode. So the initial investigation of what the measurement requirements would be used a physical channel, which I have an example of here. So this is the compliance channel defined by the USBIF for certification of hosts and receivers. So we physically measured the signals at the far end of the channel and said, yes, this is the eye stress that we want after equalization at a receiver for a compliant transmitter. And then we measured that channel with an ENA and created these S parameters of this channel that we will show you embedded into our transmitter compliance application. So the channel definitions are different from the host to the device, and obviously it's because there's different trace lengths that are required to get from the chipset to the connector based on whether it's a PC or host or a device. So for transmitter testing, channel loss dominates. So it's actually the length of FR4 that you add in the path that causes the biggest degradation or the highest amount of ISI. So if you look at a typical PC motherboard, the host package is typically 10 inches or more away from the back panel. So that dominates how long or minimum length of trace length that you'll need to get to the USB SuperSpeed connector. Then you connect up a 3-meter cable, and then you go to a device that can have roughly 5 inches of trace. So that's why those numbers exist. So the host gets longer trace length because the physical requirements of it, say an ATX motherboard, demand that. And then devices are given 5 inches of trace, which is a little longer than the 2.0 spec had defined. So here's an example of a device receiver channel test fixture set, and I highlight in yellow the parts of the channel fixtures that emulate the real-world connection. So you have the 3-meter cable, this is highlighted by this 3-meter cable here, and then the 11 inches of trace, which is on this board. It's basically a serpentine route on the FR4. So you connect the pattern generator up to the input to this FR4, connect the cable up to a breakout fixture, and the intent of the breakout fixture is to have a short path for the received signal to measure bit errors, and then you connect that up to your device under test. So once we got those channels defined and we validated that he provided the eye opening and the eye closure that we wanted to stress for the minimum eye opening of 100 millivolts peak to peak, we took that fixture set, as I said, we measured the S parameters, and then we imported that into our de-embedding and embedding tool called Infinisim on the real-time oscilloscope, and we created a transfer function. And Brian will walk you through the steps that we went through to generate that transfer function using the exact S parameters that are the official standard for the USBIF. And then on the left here, you see the superimposed waveform of the embedded signal relative to the signal measured directly through this channel. And they're almost an identical one-to-one match. Once we get that S parameter or transfer function, then as required by the Standards Committee for certification, we embed that channel effect on our transmitter measured directly through a breakout fixture that we have here. We then analyze the eye amplitude and margins and jitter and whatnot using the USB-IF SIG-test program, which is an Intel-developed tool provided to the USB Implementers Forum as a standard transmitter test software package. This eliminates the uncertainty you tend to get between analysis packages between different vendors.